So we were working on the apple, right, on the apple problem. And I asked you to determine the center temperature of the apples after 1 hour. I got 12.65. That depends on the reading that you do of the Heisler charts, right? But the value is going to be around that number. So you have the convectivity transfer coefficient, the radius of the apple, the thermal conductivity, and the thermal diffusivity. You have the time. You have T surroundings, T initial, right? So you can calculate the inverse Biot and the Fourier number that are required to read the Heisler chart. So with this inverse Biot and Fourier, if you go to the center chart for a sphere, you should be able to read about 0.79. It's kind of difficult to do this reading because it's where all the lines come together. And actually, there's another textbook. I can provide you this graph if you want. This is from another textbook that makes a zoom in that area, in that very complex area. And this other textbook provide us a zoom for that area. I can send it to your email or post it in Zoom if you would like to have access to that, that graph. I think this book provides zoom for center temperature for slab, for cylinder, and for a sphere. So I can provide the three of them. So in that case, you don't have to struggle much in deciding for a good value. So 0.79 from the zoom plot, you could read about 0.8, 0.85, I don't know, depending on how good you are in reading this area that is difficult to read for sure. So with that 0.79, you can take or you can determine the center temperature out of the definition of the dimensionless temperature, right? Because you know T surroundings is minus 15, T initial is 20, right? So we get T naught out of this equation and we get 12.65 Celsius for the center temperature. You can get 13, 13.5. I mean, that depends heavily, as you can see, of your reading. And this reading was a challenging one. So again, I will send you to your email today these three zoom plots. So you can have the center zoom plots. They are in another different textbook. So I will provide them to you. Okay, so the other question in this problem was how to get the heat transfer from each apple. So in order to get the actual heat transfer from each apple, we are going to use the third Heisler chart, that is this one, that show us the relationship between Q actual and Q max, where Q max for the case of cooling can be calculated by our general energy balance, right? Rho Cp volume delta T, where here the volume is, this B is replaced by the volume of a sphere. Okay, so essentially we are going to use this equation to get Q max, right? Then we are going to read here the ratio of Q actual to Q max, right? And then once we know Q max, we can get Q actual out of this number, out of this relationship. Okay, that's what I'm going to do right now. So first, I'm going to calculate the maximum heat transfer with our general energy balance equation, and that is rho Cp volume delta T, right? We need to recognize at this point that this rho B is nothing more than the mass. So I'm going to calculate the mass of that sphere, that is the density, 4/3 pi r naught to the third, right? We have the density of that sphere, that we take as water because it's an apple, times 4/3 pi the radius to the 3. So we have the mass, 0.3204 kilograms. So I'm ready to calculate the Q max. That is mass Cp delta T. I get the mass from the previous step times the Cp, that is something that we can get from tables, and in this problem was given, multiply it by delta T, hot minus cold at all times to ensure a positive heat transfer rate. So we get 42.76 kilojoules. Then we need to get the ratio of Q over Q max from our figure 311, our third Heisler chart. right? And in order to read that figure, we need to know the biot squared times the Fourier. So we know that the biot is 0.86. We know that the Fourier is 0.2. So biot squared times Fourier is 0.1486. So I need this value, biot squared Fourier, and the biot to read the ratio of Q over Q max from my Heisler chart. So I was able to read 0.39. If you can go, please, and check if you can read that value. You could. So 0.8 and 0.14. So let me see, because I have here. Okay. So I was able here to read a 0.39. Again, bio number, it was 0.86. So I read here like before 1, right? Between 0.5 and 1, sorry, 0.5 and 1. So here, right? And then by the square Fourier is 0.14. So it could be here, more or less. This is 1, right? So 0.14, I go all the way to the y-axis, and it's a little bit less than 0.4. So 0.39 is Q over Q max. Okay, so 0.39, and what is my solution here? 0.39, I know Q max from my energy balance, right? MCP delta T, that it was 42, we calculated here. So 0.39 times Q max is Q actual. So the Q actual is 16.67 kilojoules, right? So that's the way we use the third Heisler chart to get actual heat transfer, knowing the Q max out of the energy balance MCP delta T. So let's solve one last problem using Heisler charts, and we are going to essentially compare 3 different methods. So with this problem, the main objective is that you can see how the Heisler chart compares with the lump heat capacity approach. So we are going to consider we have a gold sphere that has 50 millimeter diameter and is dropped into a water bath that is at 290 Kelvin. If the terminal velocity is 2 meters per second and the initial sphere temperature is 400 Kelvin, how long it will take for the center line to reach 310 Kelvin? And you have several data available, such as the convective heat transfer coefficient, the thermal conductivity of the gold, the density, the CP, and the thermal diffusivity. And if you don't have the thermal diffusivity, you can calculate it, right? Because remember, the formula is K over rho CP. So if you don't have that thermal diffusivity given, you can get it. And also, there are some books that have thermal diffusivity. I don't remember if your book is one of those books. Maybe, let me check. In the meantime, you get, yeah, you have thermal diffusivity in the book. Just very careful. For example, I'm looking at your table 12 metallic elements, page 812 in your textbook. It's one of the appendix. The thermal diffusivity, it says alpha 10 to the 6, okay? But this is an engineering table, okay? So you read 10 to the minus 6. That's how you report the value, okay? So that 10 to the 6, you use it as 10 minus 6 because this is an engineering table. Okay, so first step, what could you do? Check if we can treat as a lump. So 4 seconds, 3.6 seconds, that depends on how many decimals you carry. So the density, we know it, right? The density is given. We recognize that B over this, or the volume over the surface area, is the characteristic length. And for a sphere, it can be reduced as R over 3. That is 0.025 divided by 3. That is the amount I have in here. Times the CP that is given divided by the H value that is given. The natural log of Ti, T infinity divided by T naught minus T infinity. Again, as always, I put my temperatures here. so I don't mess up, right? So T height 400, T surroundings 290, and T center 310. So I plug them here in the natural log, right? And I get 3.6 seconds as the time that it will take for the center temperature line to reach to 310 Kelvin. Now solve it with Heisler charts, please. And let me know how much you get, how it will be your time for reaching that 310 Kelvin in the center line of the sphere if you now use the Heisler charts. So same problem, same data, just redo it with Heisler charts to see what is the difference in results. To get the time out of the temperature response charts or Heisler charts, we need to get the inverse biot. Very important, see here the biot does not divide by 3. Why? Because the chart is already designed for that geometry, right? In this case, a sphere. So we don't have to correct for the geometry. Then we can get the dimensionless temperature because we have the 3 temperatures given, the center, the surroundings, and the initial, right? So with these 2 values, we go to the figure for the temperature response chart for the center temperature of the spheres. And I was able to read 0.94 as the Fourier. So your value is going to change based on your reading. And let's see, I have here 0.94. So we get dimensionless temperature 0.18, that is here down the 0.2, right? Inverse biot was 1.28, right? So 1.28 between 1.2 and 1.4, right? And then I go down, 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 and before 1. So 0.9, 0.94, 0.95, I mean, anything in between, I'm fine. I won't be fine if you read 1.5 or 2, right? Because that means that you are very far away from the actual value. So then we know the Fourier 0.94, we can get the time out of it, right? So by the definition of the Fourier, using the definition of Fourier, Fourier times the radius square divided by the thermal diffusivity give us 4.6 seconds. That is a difference of around 0.21% when using this approach. So if we compare the value with lump heat capacity approach and here the temperature response chart, our time differs or our answer differs by 21%. So again, this can help us to see that the lump heat capacity approach is a very simple approach, right? That can help us to provide reasonable answers. And most if we don't have available the book, right? What if you need to determine certain temperature and you don't have the book available? You can just make an energy balance, right? And get the equations from the lump heat capacity approach, and it will give you a reasonable answer. Well, let's see the third approach, the analytical solution. And the analytical solution implies using equations. And these equations, someone took them and make them graphs and are the Heisler charts we use, okay? So in order to avoid the use of these equations, the easiest way is to use these equations. So you have this equation 3.45a in the page 179 in your grade textbook, and is for the center temperature theta naught. 175, so if you want to check in your book, you have all these equations ready to use. 179, sorry, yeah. So you have all the equations for a plane, for a cylinder, for a sphere, right? And I'm using, obviously, the sphere, modify it for the center temperature. So as you can see, this theta naught is the dimensionless center line temperature. This tau is the Fourier, okay? So the tau is the Fourier number. And as you can see, we have two constants in this equation, C1 and sigma, right? And this constant, we get it as a function of the Biot number in the table 3.1, page 180. So in the next page, you have the table 3.1 to get those constants that you are going to use in those equations. Okay? So in order to get the time out of this equation, we need to rearrange the equation to get the Fourier number, right? Because the Fourier contains the time. So I just rearrange this equation. Again, tau is the Fourier number. To get the Fourier out of this equation, right? But what is missing here? I know the temperature, right? Well, I need to know these constants, sigma and C1. I put again here all the temperatures ready for you so you don't mix up the temperatures. So in order to get C1 and sigma, I need to get the Biot number that we already have it, is 0.77. So we go to the table and read more or less at 0.8 sigma and C1 for a sphere. So let's go to the table. I have here the table. The first two columns are for the slab. The second column, the second pair of columns are for the cylinder, and the last ones are for the sphere. My Biot number is 0.77. I'm going to read about 0.8, right? So I'm going to read sigma and C1. So those are the values I'm going to plug in that equation. Pretty straightforward, right? So these are the values that I read at 0.8 from that table. So I can get the Fourier number. And once I get the Fourier number, I can get the time. So just if we compare solutions, finally, with LOM, we get 3.6, more or less. With graphical or the Heisler chart, 4.6, a difference of 0.21%. And with analytical equation, we get 4.57 or 4.6 essentially. So Heisler charts are an easy and accurate method to solve problems. And most if you don't have available the Heisler charts. And just summarizing what we covered so far is that the LOM heat capacity system temperature can be taken just as a function of time, that we use LOM heat capacity approach. If we have a Biot number less than 0.1 and bigger than 0.1, temperature response charts provide a more accurate answer to solve 1D unsteady conduction problems. This topic, I'm just going to discuss it, and in your homework too, you will have a problem related to this topic. It's a very simple problem. In fact, I will show you that in the numerical analysis, essentially, we need to build matrix with the boundary conditions we have available, and you need to solve that matrix either in MATLAB or Excel, whatever you prefer. So I'm going to just provide a brief overview of chapter 4 that involves numerical analysis for heat conduction. So previously in our chapters 2 and 3 in the grade book, we discussed analytical methods that help us to solve the governing differential equations and provide a solution at every point in the space within the problem boundaries. In chapter 4, the author is providing us with an overview of numerical methods that help us to provide a solution only at discrete points within the problem boundaries and give an approximate solution to the exact solution. You have to remember that when dealing with a finite number of discrete points, the solution requires to solve a system of simultaneous algebraic equations opposed to a single differential equation. And this requires computer time for sure. Typically, we have different methods to discretize heat conduction differential equations: the finite difference, the finite element, and the control volume. What is the one that we use the most? The control volume, right? We define boundaries and we made balances out of that volume, right? So the control volume approach considers the energy balance on a small but finite volume within the boundaries of the problem. Very important to recall, the numerical method might give a solution that oscillates in time and space. And you need to know how to stabilize these kind of problems, right? Imagine that your solution is in this region or in this area, and maybe you are looking with your numerical another different or evaluating a different space or area, right? So you will never find the converge point for that problem solution. That is what it's talking about. So we define control volumes is what we do typically since you start, in engineering, right? You use this a lot in fluid mechanics. You define control volumes. And then you apply an energy balance to that control volume. Heat conduction into the control volume equals the rate out of that volume, right? And we establish a domain of interest that in this case, as you can see in your figure 4.1, is from x0 to x equal L, where L is the thickness of the slab we are evaluating in this case. And we define each node temperature by Ti. Okay, and what is the ultimate goal? Well, to determine all the Ti values at all the nodes, right? Because we want to know those temperature profiles, because temperature, that gradient of temperature is what gives us heat transfer, right, to occur. So then how we solve employing this new analysis, the numerical analysis? Well, regardless the problem you are considering being steady, unsteady, 2D, Cartesian, or cylindrical, you first determine the appropriate control volume shape. Then you determine all the heat flows in and out that control boundary. You write an energy balance. And for the common case we are employing in this course, that is the steady state, we make all the sum of all the heat flows into the control volume plus heat generated inside the control volume equal to the sum of all the heat flows out of the control volume. Finally, we define boundary conditions to solve, right? We typically do that. What are the three more common types of boundary conditions? First is the specified boundary condition. The second type, most common type, is the heat flux boundary condition. And the third type is the surface boundary convection condition. That is the most common one in this course, the convection boundary condition. Once we determine this, we can come to this table. You have handy this table in your textbook to build a matrix to solve that set of algebraic equations and get those TIs that we are missing, okay? So essentially is what we will be doing, building a matrix, and that is problem 5 in your homework to solve that matrix, okay? We are solving this example, and it's an example in your textbook, actually. We are going to solve it with the analytical method, and then we are going to establish the matrix so you can solve by the numerical method.